Hello everyone, I'm going to present our recent work, Facing the Randomness Certification by Quantum Probability Estimation. This talk is based on two joint papers with Mani and Hong Hao. One paper is at archive. It is a thesis-long paper. It introduces the method of quantum probability estimation and also proved many results based on this method. The second paper just summarized the main results and published this year at PR Research. So first, let me briefly introduce randomness. We want to get random numbers. For this goal, we need a device called a random number generator. The output of the device is a random number if the output satisfies the following conditions. The first one is that before running the device, we do not know the value of the output. So the output is not predictable in advance. The second condition is that when we run the generator, we hope every possible values of the output will happen with the same probability. So the output distribution is uniform. The last condition is that for some applications, we would like to make sure only the user of the device knows the value of the output. So in that case, the random number is private. Random numbers have many applications ranging from real life to scientific research. Particularly, I would like to highlight for quantum cryptography, we need private random numbers. Quantum mechanics provide multiple solutions for generating random numbers. Here, I just focus on a special way called a device-independent quantum random number generator. According to this scheme, we do not need to know how the quantum device works directly, exactly. So we just model each device by a black box. Suppose we have two local parties, Alice and Bob, well separated from each other. At each time of trial, we can provide some random inputs. After the process inside of their devices, we can read out some outputs. By repeating this process multiple times, we can estimate the distribution of the output conditional on the input. Given this distribution, we can test whether this distribution is accessible by local realism or not. For example, we can test a Bell inequality. If we see a Bell inequality violation, then the distribution can't be explained by local realism. In other words, the outputs are not a deterministic function of the inputs and any other set information, such as local hidden variable. Because of this, we can see the outputs must contain intrinsic randomness. This is the main idea behind the device-independent randomness generation, which was first pointed out by Roger Kovac in his PhD thesis. There are also other types of quantum random number generators. In general, we can think a quantum random number generator as follows. At each time of trial, we just provide some random inputs to the quantum device. According to the random input, we can prepare different quantum states or perform different measurements. After the process inside of the quantum device, we can read out some classical results. Hopefully, by running the device, we can certify the randomness contained in the outputs. Depending on what kind of assumptions are required on the device, we can get a device-independent random number generator, as introduced in the last slides, or we can get a semi-device independent or device-dependent quantum random number generator. In this talk, I will introduce a method for certifying randomness for all these types of quantum random number generators. Before introducing our method, I would like to provide some background on how to quantify randomness. To get a random number, we need a device. Here, I just call it an entropy generator. We can run the device multiple times. At each time, we provide some random input and get some classical output. Um, After finite number of times, we get a sequence of inputs and a sequence of outputs. When we run the device, it may be correlated with an adversary. Particularly, we consider quantum adversary. So after the experiments, the classical results, classical outputs and classical inputs may be correlated with the quantum adversary. We describe the joint state by a classical quantum state. Here, the adversary holds quantum set information about the classical results. In our experiments, we need to consider all the possible such classical quantum states. We call this the model of the experiment. Later, I will provide details on how to construct a model for an experiment. Here, we just focus on the case. Suppose we know the classical quantum state exactly. Then we can figure out the guessing probability. That is the maximum probability correctly guessing the output, giving the input and setting information. Once we know the guessing probability, we can figure out a measure of uniform randomness, which is called mean entropy, and the expression is given here. However, in practice, we do not know the state rho exactly. For this case, we need to consider all possible states rho prime, which is close to the ideal state rho within some distance epsilon. Then we can perform some optimization to get another measure of randomness. It is called smooth conditional mean entropy. The smooth conditional mean entropy just quantifies the amount of randomness extractable from the outputs. However, in this case, the output bits will not be exactly uniform, but there is a distance from the output bits to the uniform random bits. This distance is called the soundness error. The soundness error can be upper bounded once we know the smoothness error epsilon and also the extractor error. Because of this, so for certifying randomness, our goal is just to provide a lower bound on the smooth conditional mean entropy. So in this talk, I will introduce a method to satisfy this goal. Our method relies on one literature results. It relates smooth conditional mean entropy with another quantity called sandwiched Rényi entropy or sandwiched Rényi power. Here, I just briefly introduce this quantity. As we know from the last slides, we can describe the joint state by a classical quantum state. Accordingly, we can also figure out the reduced state of the input and the adversary. This reduced state contains all the possible set information accessible by the adversary after the experiments. Given these two states, we can define a quantity called sandwiched Rényi power. This quantity depends on a free parameter alpha. The expression of this quantity is given here. Once we know the sandwiched Rényi power, we can define another quantity called sandwiched Rényi entropy, which was first introduced by these two papers. Later, researchers just realized there is a relation between smooth conditional mean entropy and sandwiched Rényi entropy. Particularly, we can use one results by Marco Tamamicho according to these results, so the smooth conditional main entropy can be lower bounded once we know the value of the sandwiched Rényi entropy. So to achieve our goal, our task can be simplified to lower bound the sandwiched Rényi entropy. Or equivalently, we just need to upper bound the sandwiched Rényi power. We provide a measure to address this problem. Before going to the details, let me mention that this inequality has been taken advantage in previous works. One work is by Carl Miller and Yao Yunsi. The other work is entropy accumulation by Rotem and her collaborators. So now, let's see the details of our method. Our method can be summarized into several steps. So the first step, we need to construct a function called quantum estimation factor, QEF. QEF is a function of experimental results, experimental inputs, and experimental outputs. And this function always takes a non-negative value. Also, each possible state shared between the results and the adversary provide a constraint on the function. Once we know these states, we can figure out the sandwiched Rényi power. Then we can put a linear constraints on the function QEF. By constructing QEF, we are searching for a function satisfy the following condition. For each possible output and input, the product of the function and the sandwiched Rényi power take a value very close to 1. Because of this, once we know the value of the QEF, we can estimate the value of the sandwiched Rényi power. That's the main idea behind our measured quantum probability estimation. One more point I would like to mention is QEF is closely related with another function introduced in our previous works called probability estimation factor, PEF. PEF can certify randomness in the presence of classical set information. For the case of classical set information, the sandwiched Rényi power will become a power of the conditional probability. And for this case, we just need to construct PEF to directly estimate the conditional probability. And because PEF can directly estimate the conditional probability, and QEF can directly estimate the sandwiched Rényi power. In this sense, we say a QEF is a direct generalization of PEF. So according to the first step, we construct a function QEF to directly estimate the sandwiched Rényi power. So the second step of our method is just to combine the literature results so that we can provide a bound on the smooth conditional main entropy. Strictly speaking, in this step, we need to introduce some success condition before the experiments. When we run the experiments, it either succeeds or fails. Conditional on success, we can lower bound the smooth conditional main entropy. The last step of our method is for randomness generation. We just need to apply a quantum proof randomness extractor to obtain close to uniform random bits. Here I just summarize the major steps of our method. There are many details behind and also mathematical proofs for the working of the method. If you are interested in, you can read our paper. But as you can see here, the main difficulty for implementing our method is to construct the function QEF. The construction of QEFs depends on how to model the experiments. So in the next part of the talk, I will briefly introduce the model of the experiments and also explain how do we construct QEF. So the model of the experiments includes all the possible states shared between experimental results and the adversary after the experiments. Particularly, we consider such experiments. In the experiments, we can use a quantum device multiple times. So we repeat the quantum device. So at each time or trial, we just provide some input Z and get some output C. By repeatedly using the quantum device, we get a sequence of trials. So since the repeat use has a time order structure, so we get a time ordered sequence of trials. For such experiments, we can construct the model for the experiments as follows. So we first construct the model for a single trial. For a single trial, before the trial, we consider all the possible states shared between the device system and the adversary. Over the trial, we provide some random input, and according to this input, we can perform some measurements. Depending on the scenario considered, we may know some information about the measurement, or we may not know any information. Because we consider all the possible states shared between device and adversary, we consider all the possible measurements. So after the measurements, we get a set of states. So we call this the model of the experiments, a model of the trial. So once we know the model for a trial, we can combine them together to get a model for the whole experiments. Particularly, we consider a sequence of trials satisfying the quantum macro-routine conditions. These conditions tell us at each trial, given the set information contained in the previous inputs and the adversary's system, the future input will be independent of the previous outputs. In practice, this macro-routine condition is satisfied because at each trial, the input is selected according to some free randomness source. This randomness source is independent of any other random variables involved or quantum system involved in the experiments. I also would like to mention similar conditions have been used in the method of entropy accumulation. In order to perform security analysis without the IID assumption, we just use these quantum macro-routine conditions. Once we know how to construct the model of the experiments, we can construct the QEF for the model. First, let me remind you the definition of QEF. Given a model, we consider all the possible states in the model. So each possible state provides a linear constraint on the function QEF. Similarly, we can construct a QEF for a trial, given the trial model. Suppose the model for experiments is constructed under a quantum macro-routine condition, and then the QEF satisfies the following properties. Once we know the QEF for each single trial, we can multiply them together to get a QEF for the whole experiments. Because of this property, we can simplify the construction of QEF. We only need to construct QEF for a single trial. For a single trial, we just provide a characterization of the model and formulate an optimization problem to construct the single trial QEF. I will skip the details behind. I also would like to mention similar reduction have been achieved by entropy accumulation. In the case of entropy accumulation, we only need to construct a single trial main trade-off function. In our case, we only need to construct a single trial QEF. So in the final part of the talk, I will briefly demonstrate the power of our method. Uh, Here I focus on device-independent randomness generation, but as I mentioned at the beginning, our method can be applied to all types of randomness generation. Here I just list the previous demonstrations of device-independent randomness generation. You can see whether a demonstration is loophole-free or not. Also, you can compare the time cost and the number of input bits, number of output bits, also their security proofs. For example, whether the random numbers are secure against a classical adversary or quantum adversary. If you look at the loophole-free demonstration with quantum adversary, the whole experiment took about 96 hours. In particular, you can see the amount of randomness certified as a function of the time cost. You can see there is a time delay from the beginning of the experiments to the point where we can certify randomness. We call this time delay the latency. In this experiment, the randomness is certified with the soundness error 10 to minus 5. For this case, the latency is about 13 hours. If we would like to certify randomness with smaller soundness error, the latency will be larger. With our method, we can achieve low latency randomness generation in a device-independent way. We consider a particular task. We would like to generate a block of 512 random bits with soundness error bounded by 2 to minus 64. We collaborated with experimentalists at East Boulder with their loophole-free Bell-test set up. We can demonstrate our method. We performed the demonstration several times. Each time we succeeded. Here, I just list the time cost for each demonstration. You can see on average, it takes about 5 minutes for successfully satisfying the task. One particular point I also would like to mention is that for our security analysis, we consider the imperfections in the input random bits. Previous security proof and demonstration assume the input random bits are perfectly uniform. However, in practice, the input random bits can be biased. So we consider the effect of the bias. With the bias, we can still certify randomness efficiently. So with our results, here is a full list of demonstrations of device-independent randomness up to now. Finally, I also would like to comment on the difference between our method and the previous methods. As I mentioned earlier, previous works also take advantage of sandwiched Rényi entropy in order to lower bound the smooth conditional main entropy. However, these methods work in a different way as compared with ours. For example, in the work by Carl Miller and Yao Yunsi, so they figure out some randomness score function in order to lower bound the sandwiched Rényi entropy. In this step, they just use some operator inequality, and then they just lower bound the randomness score function by Bell violation. In the work of entropy accumulation, they use the chaining property of Rényi entropy and also the inequality relation between Rényi entropy and von Neumann entropy. After this step, they just construct a main trade-off function to directly estimate the von Neumann entropy. As you can see, compared with these works, our method does not use any additional inequality to estimate the sandwiched Rényi entropy. We just directly construct QEF to provide a direct estimation of sandwiched Rényi entropy. Because of this, we expect our method can perform better than previous works. Here, I just saw a specific comparison between our method and one implementation or entropy accumulation. For this comparison, I consider a task of certifying any randomness at a specified soundness error. We would like to certify randomness with as less number of trials as possible. For this task, we denote the number of trials required by entropy accumulation by NEAT and also denote the number of trials by our method by NQPE. We can compare these two numbers and particularly figure out their ratio. So this ratio is called the improvement factor. It basically tells us the higher the ratio, the more efficient our method as compared with entropy accumulation. So you can see the improvement factor depends on the Bell violation. When the Bell violation is small, the improvement factor is significant. Here, I just saw the results for the specific smoothness error, 10 to minus 6. However, we also verified that such improvement such improvement can be obtained for arbitrary smoothness error. By the way, I also would like to mention there is some connection between QEF and the main trade-off function. It may be possible to take advantage of this connection to improve the results by entropy accumulation. It will be an interesting problem to solve in the future. So with this, I would like to summarize my talk. We developed a general method for certifying randomness. This method can be used for all types of randomness generation. We also collaborated with experimental group at NIST border to demonstrate low latency randomness generation in a device independent way. By the way, I also would like to mention we collaborated with experimental groups to demonstrate the device independent randomness expansion. In the future, we would like to apply our method for randomness amplification. We expect with our method the number of trials required for amplification can be reduced significantly. We also would like to extend our method for performing quantum key distribution. We believe there is no fundamental difficulty for us to perform QKD. With this, I would like to thank you very much for your attention. If you have any questions, feel free to ask me over the online conference or just email me later. Thank you.